Hi, and welcome to EEs Talk Tech. My name is Daniel Bogdanoff, and my co-host today,
Michael Hoffman.
And with us, we have Mike Beyers, who is a ASIC planner as part of our ASIC design team here in-house. We're really excited to have him on here. I think we're going to have some great insights into ASICs today. I also want to take a quick moment for those of you who are watching on YouTube. We are now we're officially a podcast now, so you can go to EEsTalkTech.com. That's EEsTalkTech.com. And we're on iTunes, Stitcher, Google Play, all of your podcast places. If there's a podcast system that you use and we're not on there, put it in the comments of the YouTube channel. We'll make sure to get it on there.
I gave us our first rating on the iTunes store today.
Did you? Congratulations.
Yeah, 5 stars. Can you believe it?
I'm glad that you went for the 5-star thing.
I'm a huge fan of our podcast. It's pretty good. So.
Good. I'm a fan too. Mike, what do you think? You just came aware of it?
No, yeah, 5 stars for sure.
5 stars. Okay, yeah. Good answer. So, Mike, we brought you in today to talk a little bit about ASICs. We had a blog on the Oscilloscopes blog that generated a lot of comments and traction there. People were pretty interested in the topic as a whole, so we kind of scrambled to pull you in. So thanks for coming on. Maybe the first thing, if you could just give us an overview of what an ASIC is and why someone would use that in their design.
Sure. Well, it's a little bit redundant, but an ASIC is an application-specific integrated circuit, and of course it's an integrated circuit, but it really is application-specific. It's not just a slight tweak on a GPU or a DSP processor or something else that you might be familiar with. Those things in general aren't worth doing. It's also something that can dramatically increase the performance of your system, the reliability of your system, and decrease the cost of your system with an upfront cost. An upfront design and NRE cost. So you have to balance those things. In the test equipment world, right, we're relatively low volume. Well, we're very low volume in comparison to anything in the commercial world, in comparison to iPhones or Nintendos or anything. Sure. So we have to be selective with our investments. But I think that fits a lot of the world that looks out there and looks at the exploding costs of doing state-of-the-art ASICs as ASICs go from 28 nanometers to 14 nanometers and 7 nanometers. People have read, you've seen the exponential costs of working in those finer and finer nodes.
So is that when you say nanometers, that's the physical architecture size or gate size or what is...
It's a marketing number.
Okay.
So
what's the engineering number?
Yeah.
It's really the smallest thing that you can find on the ASIC, which is the effective gate length. So if you're talking about a CMOS transistor, how narrow is the effective gate, not even the drawn gate. So there's the oxide layer that is the gate. And the P or the N-type material will move under that oxide a little bit and make the effective gate a little smaller than the actual drawn gate. So in other words, it's the smallest thing they can possibly find on the ASIC to put the best number they can on their data sheet. But it is relative. Other things that matter obviously are just how big the overall transistors are, how many transistors you can fit in a square millimeter. It's up to millions per square millimeter now. But also metal layers, right? You can have all the transistors you want in the world, but unless you have enough metal layers to be able to interconnect them all, interconnect has become more and more important in the ASIC world. Which is big part of the expense of the mask sets, are these upper layer mask sets to be able to do these metal systems.
Yeah, so when we talk about this architecture, say going from 14 to 7 nanometers, does that more affect the footprint or the depth or both?
It's more the footprint. Yeah, it's putting more and more and more on the in the same area. Now, actually, bring up the word more, right? Everybody's familiar with Moore's law.
Sure.
Andy Moore, Intel. Was it the 60s?
Something like that, yeah.
Where he said, the number of transistors will double every 18 months for a given dollar amount that you can spend. And that has been true for the last 40 years plus.
Right.
And people keep talking about when is that going to end. personally, I think that somebody once joked that the number of people that predicting that Moore's law is going to end doubles every year, and I really think betting against it's a bad deal, because while the footprint continues to shrink, everybody's focused on when will that one number, when you can only fit so many atoms, right? And you can't go, you can't get any smaller. But Moore's law is not about how small you can make a transistor, how many transistors you can make for a given amount of,
Okay, so it's not a
given size. So you can grow three-dimensionally. You can change your packaging technologies. There's a bunch of things out there that I think are going to keep ASIC technology marching ahead for the foreseeable futures.
Interesting. Now, I've heard some people, about Moore's law think it's just kind of a marketing number where we're just trying to say that we've kept Moore's law, but it's kind of this thing. What's your take on that?
No, it's real. It's what's driven, the technology trends for the last 3 decades I've been in this business. The computing power you have in your phone, right, is how many hundreds of times more what they had in all of NASA when they got to the moon, et cetera.
Yeah.
And just when you think maybe things are slowing down a little bit on the technology slide, on the technology side slide, that all of a sudden new things pop up, be it the cloud, artificial intelligence, vision, self-driving cars. All these things are made possible by the just continual leaps in technology development and power. Keeping 2 things happen when you make transistors smaller.
Sure.
One is that you can compute more, but the other thing is you can do it at lower power.
Oh, okay. That makes sense.
And so power is the underestimated size of all of this. Whether you're working at the very smallest part of technology or the very largest part of technology, power is actually limiting us. At the very highest end, it's how much power can you get into it. It's how much power can you get out of a wall socket to power an instrument. It's the fact that Google is putting their data centers next to hydroelectric dams, right? They have the lowest possible power.
Yeah.
And on the lower end, it's all about battery powered, right? And how much power can you fit in your pocket and not get warm and not run the battery out before you get home at night. But in the mid range, between those 2 extremes, power is still very important because it often drives cost. That the cost of the silicon can be swamped by the cost of cooling.
Interesting.
As for a lot of applications. So it's just something worth, just something that runs all the way across. It's the other, besides processing complexity of algorithms, it's the reduction in electrical power that we draw that's key in moving these technologies forward.
So is it power, in an ASIC specifically, power woes? Is that oh man, I can't get enough power to get my gates at constant voltage, or it's a heat thing?
All of the above.
Okay.
Right. As I talked about those layers of metal, how do you get all the, power as one of the ways that as these transistors get smaller and smaller and smaller, the voltages we run them at have gotten lower and lower and lower. Right.
So you can go faster then too, I'd assume.
Yes, and when you're running a transistor all of a sudden at 0.7 of a volt, you have to worry a whole lot more about keeping that power constant and keeping noise out than you do when you were running way back when you were running your transistors at 5 volts.
Right.
And so so power integrity, thermal management, all these things are absolutely critical.
Would you say that an ASIC is a better choice for a system that you want to keep cool versus an FPGA?
Yeah, you can definitely, for the same amount of processing power, there's an order of magnitude difference between an FPGA and an ASIC, what you can accomplish.
Wouldn't have guessed that. That's a lot.
Yeah. Is that a size thing?
Again, it comes down to what I talked about, the metal system and routing signals, right? So in an FPGA, given the architecture of an FPGA and the amount of switching that's required just to route from one gate to another in an FPGA just a whole lot of extra well capacitance that needs to be driven that you can make much smaller than ASIC when you're doing a dedicated route. And so capacitance equals time switching speed is power, right?
Sure. Okay.
Yeah, the traffic system to navigate the electrons from one spot to another.
Yep.
Take up 10 times more power than the actual lane itself. That makes sense, I guess, if you think about it that way.
Yeah.
Yep.
So who else is using ASICs? So, we live in the test and measurement world. We obviously use them for our equipment. Who else? So who else, other than like phone processors?
Yeah. So there's a lot of there's a lot of emphasis on the 7 on the 14 nanometer state of the art technologies that are where the mass sets are millions of dollars. But the truth is there's a lot of technology, a lot of people still developing in the older geometries just because they're more affordable, maybe 40 nanometers, or a lot of the analog designs or mixed signal designs are in even older generations than that. Keeps the cost down, makes it so that you can make things for a lot of sensors, right? A lot of internet type things, type of applications where it's not every single person in the world has one of these.
Sure.
And I can't say for sure how many ASICs per se are in the technology, but we were talking about riding my bike in on the way in here, and on the weekend when I go.
Mike's a big biker.
Yeah. On the weekend when I go for a ride, I think I have 3 or 4 different radios, right, all talking to each other. I have my phone talking to my bike computer, which is talking to my heart rate monitor, and actually talking to a power meter, and so it's all of those and sensing direction, sensing altitude, sensing all those types of things. There's lots of work going on in integrating those types of things to make these low-powered devices possible.
Okay, that makes sense. I really want to pull the SRAM guys in here because they have, they're just right down the road actually, and they have electronic shifters. So like there was a job rec a while back in Colorado Springs for like embedded designers. It'd be really fun to bring them in, give a scope or something.
I kind of saw that one and was looking at that. But anyway.
Yeah, it's so cool. I was in the shop the other day getting something worked on, and they were just like playing with it.
I think they actually
so cool.
They actually have wireless shifting now too.
Yeah.
They went because the first electronic shifting was based on CAN, the automotive bus, but I think their new ones are wireless shifting.
Yeah, it's like encrypted and all kinds of stuff, so people can't hack into racers' gears. And anyway, I really want to bring them in. So
welcome to 2017, where your bicycle can get hacked.
Yes.
No, you think about it though. Someone's like on Tour de France, and someone's there with a little field box, whatever, like picking up the Wi-Fi signals, and think, oh, sorry, you just can't get into the gears you need to get in.
Wait, so electronic shifters are used professionally as well?
Yeah.
Yes.
Yeah,
no
big
kidding.
time. They're lightweight and they're very reliable. So they use like a stepper motor, I think, and just kind of get right on, because that's a hard part of gearing, especially if you have 10 or 12 speeds in the back, is getting that chain lined up just right. So
interesting.
Yeah. Anyway,
so your favorite ASIC application so far?
I don't know. I don't think they use. Well, they probably use something like an op amp is an ASIC, right?
Well, again, do they? One of the key things you have to ask yourself anytime you think about investing in an ASIC is, what's the alternative? What's the next best alternative? And sometimes the next best alternative is I can build the exact same thing, but it costs more. Right? If I just go through my catalog of op amps from your favorite op amp vendor and microcontrollers and et cetera. But sometimes, and at least from our standpoint, from Keysight, it's often difficult to justify just based on that.
Sure.
That we very rarely, if ever, make an ASIC that we could buy an equivalent, regardless of the cost.
Okay.
So it's that combination of not only driving costs down, but increasing performance and increasing reliability. So you need to not only be able to have it lower cost than what you could buy off, but be able to do something that you wouldn't be able to do at all any other way. And all of a sudden, that's it's easier to say, if I do this, then I can sell this many more. Sure. And all of a sudden, there's a return on investment here as opposed to just a reduction in cost. So we really almost always need both. And I don't know, I bet you if we got the SRAM guys in here, they'd say the same thing.
Yeah, that makes sense. So I forgot what I was about to ask.
I have a question, but I'm not really sure if it's going to derail us, or maybe it's just a stupid question. We'll find out stupid questions.
No pun intended about the rails.
So I was thinking about, we're talking about Moore's Law and our ability to pack more and more transistors into a certain area of space will eventually reach some sort of end. And he said there's ways around it, but it made me think for a second, a question I've never really asked anybody, let alone myself. Is there a replacement for what a transistor is somewhere down the road, right? For either switching logic or memory storage or whatever. Is at some point, like the vacuum tube was replaced by a transistor, I guess mostly in packaging, but is there like a transistor number 2 down the road at some point?
So, let's see. One of the things that people talk about is replacing electrical with optical.
Sure.
Right.
And we actually just talked about optical.
Okay,
so
which already is happening.
Shameless
right?
plug.
Right. But it used to be that you used optical only for very long distances, and now, but they went from using them only for transcontinental cables or to long distance cables to short cables around the city to even cables within a rack.
Yeah.
And they may move to cables on a PC board and eventually optical connections on a chip itself. We talked about the interconnect being the hard part a lot of times, right? Yeah. How far that actually goes, we'll see.
Sure.
The other one is, are there fundamental devices out there? And there's kind of 2 that make the news. One being the qubit or the quantum computer.
The hybrid memory cube.
The CMOS. Okay. That's a memory technology that's in this 3D packaging type arena that we were talking about earlier. But we're talking about quantum computing, and I'm getting a little bit outside of my depth here. But they have these quantum devices, and the way they interact can do computational complexity well beyond the basic ones and zeros that we can do in binary computing now. That's one. The other one I haven't heard about for a while was the fourth device, the memristor.
The fifth element. Oh,
yeah,
sorry.
kind of related to where you have a resistor, an inductor, a capacitor, and if you think about how those relate voltage to current, the fourth one is the memristor, and a little bit of work on analog design based on that. Analog should never be dismissed. If I go back 30 years ago, when I was getting out of school and coming here, all the talk was computers. Everything's going to be digitized. Analog design's not important. And everybody should be moving into digital. And that's the demise of analog.
It's a bold-faced lie. Yeah.
The demise of analog has been way overestimated, at least several times since.
That's like saying I don't need to learn how to write because there's computers now where I can type. It's like, well, everything's analog still at some point, right?
Yeah. So I think
that's an interesting thought.
We have a tendency when we think about Moore's Law to think about advances in digital computing, quantum computers, et cetera. But I think there's also possibilities in sensing on the analog side for breakthroughs that we haven't thought about or won't think about until somebody does it. Makes it obvious.
Yeah, the concept of non-binary logic is a really interesting one, especially if you can implement it on a single device like a transistor. Like that's a whole new field of computing, I imagine, that you just have to, everything now it comes down to a 1 or a 0, which I guess fundamentally you have to, but maybe there's some sort of transform that pulls you from
You're questioning everything I know right now.
0, 1, and 2 to, just, yeah. So when it comes to building an ASIC, there's different levels of, like Intel, obviously they do everything in-house. They have fabs that are billions of dollars, and they have start to finish are making a processor. Are there little guys out there or companies you can contract out to have do the whole thing for you? What does that look like?
Yeah. So Keysight has internal fabs. In Santa Rosa, there are a variety of 3.5 fabs for very high performance analog design. And we utilize those obviously in our measurements or in our instruments. But also we access a wide variety of external fabs. there's different levels at which you can interact with them. You can be total turnkey. You can find companies out there where you can just give them a drawing on a napkin, right, and give them enough money and time, and they'll turn that into an ASIC for you. If you specify it a little better than a drawing on a napkin, you're going to get a better result. But
Sure. If only we all had unlimited money and time.
But those certain people are also going to want a certain amount of volume from that business.
Sure.
Then there's houses that are partway between that and what I'll call the foundry model. Maybe you do the front half of the design, you do the logical description, the RTL, but then you turn that over to them, and then they take that through the second half of in this case, a digital ASIC design process of doing the synthesis, the back end design, even the package design, the test design, and sell you back individual parts. And then the most work on your side, right? You're taking on more work on your side, less work on the other side is the foundry relationship, where you basically are doing the not only the back end design, the physical design, the packaging design. It's kind of like being being hiring a general contractor for your house versus being the general contractor yourself.
Sure.
and getting up. You are responsible now for putting all the pieces together. What you give the foundry is the GDS, the actual descriptions of the masks. They print the masks, make the wafers, send you the wafers back. You send them out to somebody else to have bumps put on them, get them sawed up into individual die, get them put in packages, and then get them back. And maybe you send them to somebody else or test internally a lot of times the ASICs before you send them off to be put on PC boards. So there's kind of that three levels. There's total turnkey. There's somebody do the back end for you. You do the front end, and then you do basically everything but make the wafers yourself. And there's a variety of different types of technologies out there. Some of them much more affordable than others. We were talking earlier about not everything being designed. In fact, most designs are not in these 14 nanometer process.
Sure.
A lot of designs are done in older processes because they're a lot more affordable.
Now, are they more affordable like to fab and manufacture, or it's just the technology's been more vetted? What makes it more affordable?
By more affordable, I mean from an investment standpoint, from an upfront investment. The reason to go to those state-of-the-art processes is because your chip's going to be smaller and lower power.
Sure.
Right? So in the end, you might get a cheaper chip by going to those state-of-the-art processes, but the upfront process is going to cost you a lot more, not just in mass set, but in the CAD tools, et cetera. There's a lot of things that are going to get more expensive as you go to these state-of-the-art processes.
That makes sense. I know if I understand this correctly, and if you want to read through the process of how an ASIC's made, you can go check out the blog. We'll put a link in. For the RTL, which is like the gate level logic, layout for the scope or for the chip, designers will use like logic blocks where, this is a flip-flop block and I put that in, or this is a type of gate that's been made, and they drop those instead of just an AND gate and that's all they have access to.
It's mostly done any more textual, right? The RTL is a language. You can use the two most common are Verilog and VHDL, of which you can write descriptions that can be then directly translated into hardware, and that process is called synthesis. Now, you can write Verilog and VHDL that can't be translated into hardware through the synthesis process. That's called behavioral Verilog. And a lot of times you will either write that first, just to make sure that your ideas work, or let's say you're designing chip A, but it's going to talk to chip B and chip C that you are not making. But you want to make sure that all works in simulation. So chip B and chip C could be in behavior Verilog, and then you want the structural Verilog for what you're actually making. Now, the future may be in people writing at higher level languages and compile and still being able to compile, as opposed to having this very restricted thing that you can write and then translate. And there's people working on ways to translate either C, right, to be able to write straight in C or System C or a number of different things and be able to translate that into the Verilog directly. The problem with it so far is that you end up having to write your C in such a way that, frankly, from my perspective, being an old guy that's used to writing in Verilog, it looks a lot like Verilog.
Sure.
What's the benefit?
You might as well just write in Verilog.
Now so the answer to that is but it's a lot faster to do your early simulations and et cetera. So we actually use a variety of those techniques inside of Keysight for ASIC development.
Okay, interesting. Yeah, that makes sense.
What do you think the most widely produced, most high volume produced ASIC that you've worked on is here at HP Agilent Keysight?
Let's see, probably
ever in the world. What's the
the highest volume personally I've worked on here in Keysight would be, let me count, right? The MegaZoom 2 ASIC. How about that?
Okay.
I'm dating myself here.
It's like the 58 somethings.
The 54.6.
54.
54.640 42s and 622s. Okay. I worked on those ASICs.
We're on MegaZoom 4 now.
Yeah. And I worked on actually MegaZoom 1. Well, we'll go through the history if people are interested.
Yeah, might as well.
MegaZoom 1 was a combination of ASICs and DSP code written for a TI DSP, and worked a little bit on that. Actually, I worked on the DSP code, and other people worked on the ASIC. Then we moved it all.
Can you explain that a little more for me who doesn't understand what you said?
Sure. A DS.
So I understand like DSP. So when you say it was both an ASIC and code, like it was somehow manipulating signals and then feeding that into. Yeah,
we were. The actual taking data out of the A to D converter and putting it into memory was done by the ASIC. The DSP was really more of a control function.
Okay.
We didn't really use it much as a digital signal processor. It was a TMS 320 something. I can't remember the part number, but it was. It was the kind of the data control was happening out in the ASICs, and the DSP was telling things when to start and giving it counter commands, and then pulling data from it and pushing it off to the display system, which we had leveraged from the original 54600 series scopes. So we kind of bolted, with the combination of these ASICs and the DSP, kind of bolted the MegaZoom functionality onto the existing display capability of the scope. And made it kind of transparent from a software perspective.
Okay.
The software guys wouldn't agree with me, but that was a lot of work on their part too. Don't get me wrong, but from an architectural standpoint, it made it all kind of fit together. The MegaZoom 2 ASIC was where we actually then let's start from ground up, replace all the ASICs and the DSP with a new ASIC, higher sample rate, and started getting into some of the grayscale processing. And then the MegaZoom 3 was in the 54.
That was in the 6,000 and 7,000
6,000 series. Yeah, sorry, losing track of my model numbers. I can rattle off all the project names, but I can never remember the model numbers.
Secret project code names.
And then the MegaZoom 4 ASIC was moving to a more modern technology and some of the new functions like the zone trigger, et cetera, and as well as moving to a new technology got us lower cost, lower power.
Sure, that makes sense. Okay, and we're actually out of time.
Oh wow. You're right. That does go fast.
Yeah, I know. Mike was a little nervous before we started. Mike Hoffman was nervous.
I was nervous?
No. It just goes so fast. So we'll have to have another episode with you on, I think.
Okay.
I think we're going to do that. Normally we do a predictions section at the end. We may forgo that this time because I didn't prep anyone for that. Mike, do you have a prediction? Mike Hoffman, put you on the spot.
Mike Beyers will be a key part of creating MegaZoom 5 at some point in the future. At an undisclosed
there you
date.
Go. Okay. Redacted. All right. Make sure you subscribe to the EEs Talk Tech podcast, iTunes, Stitcher, Google Play, whatever your favorite podcast engine is. Also, you can check us out on YouTube. We have new videos every other week, kind of depending on the week. But consistently videos coming out on the Keysight Oscilloscopes YouTube channel.
Rockstar.
You can also check out our blog. You can follow me on Twitter if you have questions. Put them in the comments on podcast video. You can ask me on Twitter, our Facebook page, our Instagram page, whatever you want. There's a lot of ways to contact us. Thanks, Mike, and we will see you next time.